Okay, for people joining this live stream, we are looking at some design reviews for the upcoming version 13.1 of Autumn Language, and we are talking today about machine learning. I think we have more than one design review today. First one here is about machine learning. Okay, we've talked a bit about feature impact plot before, haven't we?
Yes, during our check-in meetings. So those are going to be the biggest new feature.
It has the biggest impact and it's the biggest new feature, and that's why it's called the feature impact plot.
Exactly. And we hope to show something. That's why it's called plot.
Right. Okay, let's take a look here. I really wish you wouldn't do that. I really wish you wouldn't do this. This putting multiple things on one line like that.
Oh, yeah, I split the others. I forgot that. Sorry.
I mean, I don't know whether that, I suppose in this particular case. Okay, what are you really showing here? Let's take a look here. So really, why don't you put an iconized piece of data that exactly is of the form you want, so you don't have to mess around with a lot of stuff? Or maybe you'll have to anyway. I don't know.
You need, it's after train. You need a model. I could put a train model there. I could just start with model equal the output of a classifier. Model equal the classifier function.
No, I think this is good to show the classifier. I think. Okay, so let's understand what this is doing.
Mm-hmm.
Oh boy! So you've got an actual word impact that you're putting in there.
Yeah, we are going to remove. We are going to remove the label. I was discussing this with Roger. We
it's
don't
a
want
bad
to.
idea.
Generally speaking, these functions are probably a week away from being fully cooked, like you would expect them to be. They're close, but they're not fully
okay,
cooked.
all right, fine. So what we're showing here, I don't really understand this.
If you scroll up to the beginning of the notes, I tried to put like a very simple example at the beginning. So what we are showing is for each example you give, and if you select the feature you select, we show the feature on the horizontal axis and the impact it has on the classification or prediction on the vertical axis. So for example,
this is completely obscure. This can be explained better.
I agree.
This is...
Yes.
Okay, so what are you actually plotting? You're plotting the value. Explain this plot, please.
Okay, so there's one point, one dot for each example.
I got that.
On the horizontal axis, there's a value of the one feature that you select. If you want multiple features, we are going to have multiple plots. And on the vertical axis, there is the shaft value, technically. And
no, but tell me what that means. So
that means how much it deviates from its
exactly
mean.
So
so there's a mean value. Let's say that you didn't have this example. What would be the value, basically? And if you have this example, how much does it add to it or subtract to it?
From what? From...
So like if you don't have...
If that SI is 0, it means that example had no impact on the feature. It wouldn't change the value.
What do you mean on the feature?
No, on the result. On the result.
On the result.
What result?
Of the classifier, of the predictor. So I'm predicting
all
something.
Possible results. Well, what are you predicting?
I'm predicting. So you give me one person. I want to predict the credit score.
Okay, fine.
So what is the impact on its age on the credit score? It's a positive impact or it's a negative impact?
Okay, so you should say... Okay, so what this is doing is it's plotting and I don't understand what this is doing.
Oh, because there's a classifier. It has more than one class. So there's the impact for the free classification, which is not the same.
Okay, so you're not making that clear in the... Okay, so in the first case, Okay, so what this is showing, if we cut out the three things, because that's already confusing.
Well, you can look at the one below. There's a single class.
I understand that, but I'm saying in the examples, don't give the three case first.
Yeah,
Right?
yeah,
So
yeah.
the case to give first is, I wonder whether there's something with synthetic data where it's really obvious what's going on.
And also, it's really simple for predict because predict has one value. So I'm saying, how much would this perturb my value up or down? Because in the classification case, we're dealing with probabilities or really log odds.
I should invert predict. If you scroll down, there is example for predict. That should come first. It's much easier.
Except it didn't even get the result.
No, it was there. I don't know why it's aborted.
Okay, all right, fine. But
it was looking like one of the four that you see in the grid. It's a single feature that affects the result.
Well, that's what you should explain first.
Yeah.
And then you should say, here, plots it for a predictor. Okay. And then you should explain that for a classifier, it will show, by default, it shows each, give the signature here. By default, it shows all of the classified, all of the possible classification outputs, right?
Yeah.
Correct. And then, or you can specialize it, which is, I think, what you're doing here. Is that right? Yes. Right. So you've got to show that signature up in the main documentation block. Does that make sense?
Makes sense. Yes.
And let me just try to understand. So you're showing for a given data value, you're showing what value of this feature did it have? What value does it have of that feature?
Yes.
And so the big picture is, this is a way of characterizing the effect of a given feature on the result.
Exactly. So the impact, it's a plot of the impact of the feature on the result.
Okay, so this is really hard to understand. And this is really hard to understand, right? And this is also very hard to understand. Mean values and so on, that's hard to understand. Use predict, as Roger has said. So it's literally the value, how much does this have, what effect does this have on the predicted value? Isn't that correct? That's what this is in that case.
Yes.
No, that's not the predicted value. It's the deviation. I mean, we could add the predicted value and not say it's zero.
No, it is. No. Well, we could do that too. But this is the change in the predicted value, delta prediction.
Exactly. Right? It's a delta. It's a delta right
now. Delta on the prediction associated with, and you should say that. I mean, this is utterly obscure here. This should say, now again, if I remove one of these points, it's saying how much the value will change. Is that correct?
It's not really if you remove a point. It's like if that feature were missing, you would stay on the horizontal line. Because you have the specific value, that example goes down or goes up. So it's about the feature. If you don't have, if the feature is literally missing, then you stay, you just use the average. But because we have a specific value for the feature, we have a different result.
No, but I don't understand. What's the significance of each individual example?
Oh, the example are providing some distribution because you need examples to see what's going on.
No, you're not explaining this. Okay, let's go through this again.
Okay.
You got a bunch of dots. So what we're saying is.
So what confused me, Stephen, is this kind of like a parametric plot where the parameter is example. So for each example, we get a feature value and a feature impact.
Yes, I understand. So this is implicitly showing a distribution.
Yes. And keep in mind that each example has other features that you don't look at here.
I understand. That's not relevant to this. This is saying, what is, here's a way to explain it. What is the distribution of effects on the value? Okay, so let me try and write it as I might write it.
Okay.
Okay. So it shows the distribution of effects on the output contributed let's see, contributed by examples with different values of a given feature. But that's not quite right.
The thing is that the examples are like a proxy. They're not so important per se.
Well, so you're just showing the distribution. Okay. A distribution of effects on the output of associated with data, effects on the output okay, so it's basically how much effect does this feature in the data have on the output?
Exactly.
Okay, so if we lead with that somehow, shows the, I mean, it shows plots there's a plot illustrating the effect that, and so let's see, what's the arrow thing first of all? Yeah, the first arrow thing, that's of, okay, so let's say we say, okay, so if we say, hold on, if
we are actually experimenting with a different syntax to avoid the double arrow to use the feature in the second argument, which is
okay,
it's
all right,
nicer.
okay,
but it's, yeah, that's a detail.
Okay, all right, data.
Let's say data comma feature.
Is it data or is it the model?
Sorry, model. Sorry, I was distracted.
Model comma feature gives a plot illustrating the effect that, let's call it feet or whatever, that,
oh, you must say the feature feet has, okay.
Yeah, the feature feet
has on the output.
Wait. No, wait a second. Has, hold on. Has on the, that's badly said, but I mean, and gives a plot illustrating the effect that I mean, it's roughly this, is it not?
Yes.
Right, the effect that the feature for a trained model, whatever it's called, of the feature feet in the underlying data for a trained model mod has on the output of the model.
Okay, gives a plot of the impact of the feet.
That the feature feet
okay, this
in the underlying data for a trained model mod has on the output of the model.
Yeah, it still makes sense, yes.
Actually, what it is, it's not really quite this. It's not as the impact that the, okay, a better way to say it might be that the values of the feature feet is that right? Or is that not right? I mean, because you're plotting in the end.
No, it is a value. Yeah, it is the presence of the feature with that specific value.
Impact. The values of the feature feet and the underlying data for a trained model have on the output of the model. It's not terrible. It's not terrible. And then you can go on and use the
yeah, I can introduce data to give like some specific data you want to use for the test. And
well, I mean, is it the case that you could make synthetic data where
this is exactly what happens? This is why the first argument doesn't have data.
No. I'm saying no, but what you're doing here is when you make that plot, you're taking all of the training data from the model, right?
I'm using the missing value synthesizer of the model to generate the static distribution.
God, really? So that's fake data?
Yeah, it's synthetic data.
What the heck is this? What the hell is this plot?
But
I don't understand. I don't understand. Why are you not doing what you're really trying to plot is a distribution? This is a really confusing plot. If that's fake data, I thought that was the real data that was used for the training of the model.
Well, that's not stored in the model. That's lost. If you have it, you can pass it and see the effect of that. But what you are studying is on the data, is the model, is how the model reacts on some input.
Okay.
And the sentence is
wait. It's not correct. This is bullshit.
No, why?
It's not correct. It's just not correct. It's giving the sense that this is underlying data for a trained model, which to me suggests the original data. Gives a plot of the impact that the feature feet in, okay, wait a minute, that the value of the feature feet in a, oh yeah, look, here's a way to do it. The impact, the value of the feature feet in input to a trained model will have on the output of the model. Value. Here's the plot of the impact, the value of the feature feet in input to a trained model will have on the output of the model. I believe that's correct. And then what you explain is that you're using, how you indicate that plot. It's the value of that feature in the input. So in other words, if I've got input that has that value of the feature,
yeah, it goes to that. But
I'm expecting that it will have that delta. So if in a vertical slice here, I have a certain distribution, that's going to give me the probability distribution
exactly
for that feature value of
that
of the change in the output.
Yeah, and the spread is due to the other features.
I understand. So if I were to do a very simple thing here, if I were to make a model where it is a trivial model, where it just gives me the output is, a linear function of the feature value, right?
Yeah,
Then
for a
I
linear
should just
predictor with one feature is a line, for example.
Yes, right. So you should show that.
Yes.
You should show that, and then you should say if there are other features. If there's one feature, right? If the whole data is just one feature, if this is just a function, right? Okay, so the first thing to do is to show if it's a function of one variable, f of x, then this picture is basically a picture of f of x. Is it not?
Yes.
Okay, so show that first. Okay.
With some offset due to the average, but yes.
Yes. Right. So show that first, then put another feature in there and say, now there's a distribution for every point.
Yeah, it makes a lot of sense, actually.
Right?
Yeah.
Okay, then people have a fighting chance of understanding what the heck this thing is. Okay, should I save this notebook somewhere? Yeah.
Please.
My gosh, why do I not have machine learning? Well, I have neural net framework. Okay. So feature impact cumulative plot. Really? We've got 17 versions of this incomprehensible thing?
Well, they show different things, which might help. Actually.
They're incomprehensible in different ways.
Exactly. It's like the shadow
impacts you. Impact.
Oh, it's not built, so it's not going to be there.
Oh, well, okay. So maybe you can show this to me.
No. It is in CDS.
It's in the source.
It's in the source. Yeah, same. Oh, you can use if you scroll down, there's a related link. The first one. It's going to be that. Yep.
Oh my gosh. What the heck is this?
Actually, this is very nice. It's basically the.
So if you have feature 1, 2, 3, how much do they cumulative impact? Do you see what I'm saying?
If you can sort the features in a certain order, as you go down from the least impactful to the most impactful, or maybe the other way around.
Yeah, the other way around, yes.
That would be pretty good, yeah.
Yeah, it shows basically for this prediction of the wine quality, first volatile acidity is splitting the data set a lot. Then I add alcohol and I have other splits, and then more and more and more. And at the bottom, I fall down on the final result.
Okay, so what this is a parallel axis plot, basically.
Yes.
Yeah, if you scroll down,
vertical parallel axis plot.
If you scroll down, we have the version implemented with parallel axis.
Okay.
It's just that we don't have a vertical one, but yeah.
We'll get one.
Yeah, exactly.
Okay, I understand. So then that would say, is this again synthetic data?
No, I'm passing it this sample, for example. With a 2-argument form, I use a sample. So if you pass one sample
in feature impact plot, can you give it actual data as well?
Yeah, in all of them. So you can actually analyze one example if you want specifically.
In this case, if you analyze one example, you get one dot.
Yeah.
Exactly. Not very informative.
I mean that syntax there doesn't have the data, right? So
I know. Okay. I don't think it's bad to have. I think it is better to have the multi-arrow thing than it is to have the data off in the 17th argument.
No, I agree. What I was thinking that when we talked about this, because there are two things that it branches on. There's model and model plus data. So that should be in the first argument.
Mm-hmm.
But then we have, what was the two things in the second? There's feature and
class.
Feature and class. Yeah.
So it's just feature for the predictor and feature and class for the classifier.
I'm not sure that the data. Okay, but what you've got to explain here. Okay, feature impact cumulative. Are you sure it shouldn't be called cumulative feature impact plot?
I mean, we created a family of names that was like kind of mirroring each other to suggest that they are for the same purpose.
I understand that.
I'm open to.
But I mean, to me.
Well, this is not the cumulative version of the feature impact plot. This is a cumulative version of the summary plot, actually, which you might want to look side by side. So this is a non-accumulated version of the other one. So you just look at the pure Sharp value here. So you can see the distribution of Sharp values for all the features. So compared to the original feature impact, you lose on some because you don't see the feature anymore, but you gain the insight of a data set, of a full data set.
Okay. So this one is much easier to explain.
Yeah, kind of.
Yep.
This one is the effect on the value for every data point.
Mm-hmm.
It's the effect that that feature value
Mm-hmm.
has on the final result.
Exactly.
Don't we already have this? Isn't this some Sharp values thing? Isn't this exactly what we've already got?
It is. We are promoting this to top level and adding a full family of functions to do interpretive machine learning. But that was an obscure property of classifier measurement. Now is a fully fledged visualization function.
Maybe, I mean, this one is the least incomprehensible in my view. And also it's the one where you're going to put all of the data in. Wait a minute. These features, they're not necessarily named, right?
No, it could be F1, F2, F3. If you don't give them, you can pass a feature names to specify the name afterwards. But yeah, if you don't know what they are, they're just going to be feature 1, feature 2.
Okay. And I'm a little confused about the X scale for each of these features. That is, if I'm looking at this plot and I want to compare.
That's the impact, yeah? It's not a feature, it's the impact. So it's the same scale on each axis.
I see. Okay, so this function okay, let's go through these again.
Mm-hmm.
I think it's super confusing. These functions are named as similarly as they are.
Okay. We have a super long list of alternate names for all of them because of this reason. So this is the only different one.
Oh,
Where we don't have
the only different one of all
Yeah,
four
exactly.
that are each different. We've got an even more different one.
Exactly. Well, because this is the only one that is not using sharp values. This is plotting the model output directly. So, for example, this is a survival probability given the age for different people.
Okay, these are crazy, if I might say so. Okay, so first of all, okay, let's describe what these are.
Mm-hmm.
Wait a minute. What is this? What is this? This is plotting. This is the distribution. Is that correct?
Yeah, this is a logistic regression. So it's it's a probability. The probability of survival is going down with the age. This is what is called in the literature ICE plot, individual conditional expectation. Just to say that I'm not making this up.
Okay, so walk me through again what this is. So this is what are these different curves here?
Like they are the examples that I'm passing. So each example we have different class on the ship and a different sex. And what happens if I take it and I move and I vary? So I have basically what happens if I take different people and I change their age, leaving everything else constant.
But you've only how did it know to pick 4 of those?
No, I passed 10, but some of them are the same sex and class, so it collapsed to 4. I did a random sample of 10.
Okay, wait a sec. Wait a sec. But the number of data points here is just 10. Is that right?
Exactly. So it would be like I would have 10 lines, but some of the lines they are on top of each other because they are the same.
So in the model, okay, you could have taken a person with a specific age who has various features that are, okay, so all features are determined except one feature is being varied.
Exactly. So this allows you to see groups. Like in this case, like no matter what the other features are, there's a downward trend with age.
You know, I hate this stuff so much. You know, I was planning like 30 when we first built first version of Mathematica and Wolfram language. I was planning to try and clean up the field of statistics and not to have all of this kind of telling jokes by numbers nonsense, where you know there's just some we've got an ANOVA plot with this thing and that thing, and you know if we just compute the such and such value. And then you run into people who say, "Oh yeah, I'm really interested in the blah 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 value." That's the indicator I always pay attention to. And I thought maybe we could clean that up and have things where we could actually explain what was going on. And I gave up because it seemed like people just, you know, you talk to people who use that stuff, they just say, "Oh yeah, I use the ranked Wilcoxon test. That's the thing I really like." It's like, what is it? And they say, well, I don't know. I kind of learned about it ages ago in some statistics class. I've long ago forgotten, but that's the thing I always look at. And it's just like, you know, people who assess companies will say things like, you know, for stock trading and things, they'll say, I always look at the blah, blah, blah thing. So what's my point here? My point is, if these things have names in the literature, but they're frigging incomprehensible, you know, maybe the only use is people who already know, you know, who already learnt in their, you know, whatever. Oh yeah, I should really care about the ICE plot or whatever it is.
Well, I think there's some added value, like maybe not for all 4 of them, but like for example, the cumulative function, I think it really explains very well where each example is going feature by feature.
What are you saying? You're saying the plot is good, or you're saying that the name is? Look, the question
No,
is.
I don't care about the name. In this case, I'm saying that the plot is informative.
I think that this will be used
all
largely in the
plot
same
is.
way that the things are used in statistics as a report that says, hey, this is a good model because look at all the corroborating.
I know, but so what does one do in
indicators.
statistics in that regard? I mean, to me,
But
I always
they
avoid
usually,
that stuff like the plague. I always try and get, an explicit plot where you can understand what the plot is of. And whenever it's
yes.
something incomprehensible, it's like a wimp out. It's like people who write, it's like, yes, you can put a soup of words together and maybe they're trying to say something, but it takes a lot more effort to get that collection of words to be clear. And similarly, people can say, well, I put a plot, it's in my paper, it's in my report, whatever. Be happy. But the fact is, with effort, with real effort, you can unscramble it to the point where it's a very clean thing where, you can explain exactly what the plot is of, but most people can't be bothered. And they just put in some random plot.
Yeah. I mean, as you correctly pointed out now, and I said too, this is not quite cooked in terms of us explaining it or the aesthetics, or there's a lot of things that needs a little bit more.
No, I understand. But I'm
Okay.
asking about the principle here of, okay, like a histogram, okay?
Yeah.
People understand the idea of a histogram, and then there are lots of tweaks to it.
Sure.
A quantile plot. I don't know. Some people understand that. It's not too hard to understand.
Right.
By the time you get into some of these some kinds of plots, like, for example, a parallel access plot, not too hard to understand. The question is, are these plots, can we get them to the point where they're consumer understandable? And our best chance is in the name. What's an example of another kind of plot where, a lot of kinds of plots we have, okay, these indicator
How
plots.
about non-parametric smooth kernel density estimator? We don't use that name, but that is a name used. Then that's basically smooth histogram.
No, I know. But calling it a smooth histogram, what do we call it in fact?
I think we do actually call it a smooth histogram.
Smooth histogram, that's what I would think. Yeah. It's like, that's what people think of it as. And right. Yes, it's a kernel density estimator, blah, blah, blah. We've had some trouble in the spatial statistics area also with these slightly incomprehensible things, which I think we managed to iron out.
Well, yeah. If you want to drop the whole naming scheme, the cumulative one is called waterfall plot, which makes a lot of sense.
No.
But
no. That has to do with particular layout.
Yeah. No. Look, let's try and understand, what could we call these plots? We're starting from scratch, and let's start off with this one.
Okay.
This one is, that one basically is, let's just see, it's some kind of feature.
I can bring up, we have super long list of these names.
Okay, explain to me in one sentence, what is this plot? I already know, but tell me what your one
is it the dependency of the model result from a specific feature value. Or
okay, so
even better, how the model the result of the model is conditioned, depends by a specific feature value.
Model feature dependence.
Okay, so it is roughly a feature value dependency plot. Is it not?
Yep. Other names we had for these were, feature dependency plot, feature prediction dependency plot, feature partial dependency plot, and all the family.
Okay. Feature value dependency plot. Okay, what would this, okay, then in that family, if we're just naming them by what we think, so let's talk about the cumulative one here.
Okay. That's the accumulated feature dependency plot.
No, it's not. It's not. Well, it's not a feature dependency.
No, it's not value.
Oh, no, right.
I drop value.
Right.
Well, there's no dependency though here. There's more like there's impact or effect or something like that.
I see. Okay, so this one here.
That could also be called feature impact plot. We call it summary because we didn't know what to call the other one, but this is a non-accumulated version of the other one. So if you drop accumulated, that's the feature impact plot.
You meant, yeah, exactly.
Yeah.
But that's really a list plot, isn't it?
Yeah, also the first one is. Actually, this is a chart, distribution chart with a custom display function. But yeah.
There are other ways you could show that too. That we have.
Well, with little histograms and things. Okay, so in this case,
exactly.
okay, so the most incomprehensible, the thing you were calling feature impact plots here.
Yes.
What really is that?
So this is the super detailed one. So
you
this is
zoom in, yeah.
Yeah, this is as zoomed in as we get, right? Pretty much.
Well, no, but it's the feature impact plot. It's this one here.
Yeah, where I take only one axis and I expand on the other axis, I put the feature value, which here is not present. So is that single axis, spread over with the feature value?
Oh, feature value impact plot. Impact.
Yeah, impact.
Huh, yes.
Now, you could imagine doing that in more than 2 dimensions, right? You could imagine 2 features, could you not?
Oh, yes. You mean instead of putting the 2 plots side by side, you just do the 3D version of that. Yes.
Well, no, but this is okay. Feature value impact plot. Okay, so this one, so this okay, feature impact plot here. Shows the effect, the impact of the value of each of the features on the result of a model. So the features of
the value of each of the features on the result.
Each of the features in the data, each of the extracted features in the data on the result of a model.
Each of the individual features, maybe.
Yeah, okay, that's nice.
because we are like splitting them apart here.
Okay, shows the impact of the value of each
individual feature,
or just each feature.
Yeah.
Well, in the data, so you're actually going to give the data probably, in most cases, in the first signature here.
Yeah, I could have the data in the first signature and then drop it. Yeah.
Yeah, right. So then here, this is saying, well, shows the cumulative. Then this would then say, shows the cumulative impact of the value of each feature in the data on the result of a model.
Yes.
Okay. So here, shows the dependency of the result of a model on the value of a particular feature in data.
Yep.
Okay. Okay, this one here. Dongs on our live stream is commenting, really feels like you could replace feature with parameter and have something that would be useful in classic regression. That's an interesting claim, that we could apply this also to our regression stuff.
Yes, probably
well,
could.
that if you scroll up in the first page that you have here, we can convert a fitted model into a predictor and use it here.
Yeah.
No,
So
but what this person is pointing out is that with our very traditional regression stuff.
Yes, but that's what actually Julio's already done. So fitted model can be used as input.
Oh, I see. Great. So the only question is the name feature, which is not what regressionists use.
Right.
They use parameter.
Yeah.
I don't think that's terrible. I think feature is the modern parameter. Do you agree? I mean, that's my impression.
I will add an example for discoverability that says, show the dependency of the
absolutely, in regression
parameter.
Right. Okay, but we also put this on guide pages. We're talking about regression. Okay, let's do this, and then we got to wrap here. Feature value impact plot. Okay, this was an interesting exercise, by the way, trying to grind this into something that is even vaguely comprehensible.
Well, thank you. You just saved an hour or several hours of my time, probably.
Right. Okay. Well, let's see whether we can nail the last one. Okay. So feature value impact plot. Okay. Shows, actually, we want to say all of these want to be plots. Give some plots. Blah, blah, blah. Okay. Plots the impact of the value of a given feature on the results of a model. Is that correct?
Yeah.
That's pretty simple.
Yeah.
It's getting closer to what is actually there, but
what's the impact of the input feature?
Yeah, this one we have now here, I think, as better.
Of the input feature values is a bit. Yeah, I mean, this is better to say feature value impact, feature value impact plot.
Yeah.
Tells you it's the impact of the value of a feature.
Exactly. It's pretty descriptive.
Okay. Well,
They
I think
still sound like a family.
Yeah, I'm not too worried about that. I think that
and actually, the one that is plotting a different thing has a different final name in the third place, which is nice as well.
What do you mean?
But the dependency plot, it doesn't have impact, which is nice.
All right, I think we got it. Okay, well, so I'm afraid we're going to have to go on with a separate meeting.
Okay.
For the other things that, go ahead.
The rest is a lot smaller. So I envision it's going to be probably when I implement this stuff that we have here, we can probably review this quickly and then go very quickly through the rest.
Okay. I mean, clearly we need to talk about, but not. Yeah, I mean, right. There's more strategic issues to talk about.
Exactly. But that's it's not design review for 13.1. It's more like exactly strategic directions.
Fine. Okay. Good stuff. All right. Thanks very much. And